Okay, so we often hear claims like a successful theory of quantum gravity must recover general relativity in the relevant domains, or that space-time should emerge from quantum gravity if the theory doesn't feature it fundamentally. And as these sorts of claims indicate, the relationships between quantum gravity and GR play a role in defining criteria of acceptance for a theory of quantum gravity. And as I'll show, they thus play a role in defining what quantum gravity is. So far in the philosophy of quantum gravity, there's been quite a lot of talk about the idea of emergence. However, there hasn't been much of an attempt to connect this to broader emergence literature in philosophy of science. Also, it's not just emergence that are the branch of inter-theory relationships that are important in this context. There's also reduction, as we've heard from Josh, and correspondence. So my main aim today is to provide an account of each of these types of inter-theory relations, showing that they are useful for different purposes in the context of quantum gravity. I'd like to start to take the focus off of emergence and try to encourage more refined discussion in terms of different types of inter-theory relations. Also, finally, I'm going to show how emergence in quantum gravity, the conception that's used, relates to other accounts in broader philosophy of science. So this work should be useful for understanding the relationships between our theories, but also the process of theory development and theory change. And also part of my broader project is trying to understand the principles of quantum gravity and how these can help us in the search for a theory. So that's the long-term goal here. This is just the start, work in progress. Okay. So I'll start by first explaining what I take quantum gravity to be. I'll then present my account of fundamentality, so what it means for a theory to be more fundamental than another. I'll then reacquaint you with the two main conceptions of reduction that are important in philosophy of philosophy of science more generally. I'll then go on to correspondence, come back to reduction, and then argue that it's just a special case of correspondence relations. And then finally at the end, I'll talk about emergence. So I made a little status bar along the bottom so you can follow along. So what is quantum gravity? I take it that it's any theory that satisfies the criteria that are taken to define quantum gravity. So these are called criteria of theory acceptance or criteria of theory success. One of the biggest problems in quantum gravity, of course, is that there is no established set of such criteria across all the different approaches. And instead, we have this plurality of different approaches in part because they adopt a different set of criteria each. Not only this, but they each have different interpretations of each of these criteria. They also have different guiding principles and different interpretations of these, and so on. However, I take it that there is one key shared criterion across all the different approaches to quantum gravity, and that is the requirement that the theory describe the domains where both general relativity and quantum theory are expected to be necessary. So of course, at the Planck scale, for describing black holes, and for cosmological singularities. Okay, I also take it that the minimal agreed upon set across the different approaches should include at least these following three criteria as well. However, careful, because while I think these are the least controversial ones to include, they all have different interpretations of these and how they should be taken. So I've been very purposely vague in presenting them here. So there's the requirement that the theory recover GR in the domains where GR is known to be successful. There's a requirement that the theory take account of other current established theories and frameworks, of course quantum theory, and by take account of, I mean that the theory itself is quantum in some sense, or beyond quantum, or that it recover particular quantum field theories, whatever is necessary here. Finally, I also take it, very hopefully, that there's a requirement that the theory make novel, hopefully unique predictions that are subsequently confirmed by experiment or observation. However, it's been suggested to me that perhaps this is too strong a criterion. Nevertheless, my project today is to start to understand number 2 and number 3 and how these serve to define quantum gravity. Oh, sorry. All right, so fundamentality. Here I'm just interested in relative fundamentality. So a more fundamental theory M for more fundamental, of a given system S or phenomenon P provides a more basic description of the system or phenomenon than does a less fundamental theory L for less fundamental. And I take it that there's only one condition for a theory to be more fundamental than another, and that is that the laws of the less fundamental theory depend in part on the physics of the more fundamental theory, but not the other way around. So my account of fundamentality is a bit unusual for a couple of reasons. Firstly, I don't take it to be necessary that M, the more fundamental theory, has a broader domain than the less fundamental one. An example here is atomic theory, which is less fundamental than quantum chromodynamics. However, QCD is more restricted in terms of the systems that it applies to. However, the idea of a more fundamental theory having a broader domain than a less fundamental one is important in understanding reduction. In the case of atomic physics, we wouldn't say that it reduces to QCD, but rather the physics of the whole standard model. And I'll return to this when discussing reduction. Also, I don't take it that a more fundamental and a less fundamental theory are necessarily on different levels. The example here is special relativity, which is less fundamental than general relativity, but they're on the same level of description. However, the idea of different levels is important in understanding emergence. And in this example, we wouldn't say that special relativity emerges from GR, precisely because they're on the same sort of level. But I'll return to this when discussing emergence. So, in the case of quantum gravity, there are two ways in which quantum gravity is more fundamental than GR, and each of these is sufficient to satisfy my criterion of fundamentality. Firstly, that the theory be quantum or beyond quantum in some sense, and secondly, that it be micro. So note that, interestingly, these are both ways of viewing quantum gravity as being on a different level to GR. And so we have a conception, well actually two conceptions of emergence here. Also, these two ways of being more fundamental correspond to two transitions, as Josh pointed out. There's the quantum classical transition, by which we recover the classical appearance of a fundamentally quantum space-time. There's also the micro-macro transition, by which we return to accessible energy scales. And already there's been a lot said about these transitions in the literature, so I'm not going to discuss them today. Okay, reduction. Two senses of reduction that are important in philosophy of physics. The physicist's sense, the philosopher's sense, which is reduction 1, and the physicist's sense, which is reduction 2. And please don't be offended by these labels. They're not intended to imply that these are the views of all physicists or all philosophers. Certainly not. They're just handy ways to help you remember which one's which. So reduction 1, it holds that the less fundamental theory L reduces to a more fundamental theory M if the laws of the less fundamental theory, or a corrected version of, can be deduced from those of the more fundamental theory. Prime example being Nagel reduction, but also variants such as Nagel-Schaffner reduction. They're quite well defined formally. Unlike the physicist's sense, so reduction 2 goes the other direction. We say that the more fundamental theory reduces to the less fundamental theory, or corrected version thereof, in the domains where the less fundamental theory is known to be successful. And there is no general account of reduction 2. What's clear is that it involves numerous and various approximation and limiting relations. It may feature a characteristic limiting relation, but it's not restricted to this. So most people tend to associate it with this, but it's not necessary. Also, the physicist's sense of derivation is used, which is typically less rigorous than the mathematician's one, certainly not logical deduction. So reduction 2 is broader than reduction 1 in that it's not restricted to logical deduction. It's also weaker than reduction 1 because it's not restricted to anything like the Nagel-Schaffner schema. Okay, before moving on, I've got to say it's debatable whether reduction 1 holds, or at least whether it holds as often as it's kind of thought to or required to. Also, in the case of reduction 2, it's debatable whether the relations of reduction 2 actually demonstrate that M turns into or recovers the older theory in the appropriate domain in any particular case. And one of the reasons for this is that typically not all of the laws and equations of the two theories are involved in these reductive relations. Instead, it seems like reduction is taken to hold when the relations that are articulated between the two theories are enough to kind of just convince us that reduction holds in principle. Sorry. I need a bigger ledge up here. Okay. Yeah, I'll return to reduction, but for now, onto correspondence, which is, of course, most familiar from the correspondence principle, which states that quantum mechanics reduce to classical mechanics in the domains where classical mechanics is successful. So obviously here we mean reduction 2. However, I take it that we have an even broader notion of correspondence that applies, or includes any relationships that link any two theories, so not just a more fundamental and a less fundamental one, any relationships that link them in the domains where they both apply. And when I say the domain applicability, I mean the domain where they actually successfully describe, known to successfully describe, that are taken to establish or intended to establish the consistency of these two theories in the shared domain. Consistency meaning that the two theories both have the same results in this shared domain, and by results I mean theoretical propositions as well as observational ones. So, stated this way reveals the concept of correspondence as tautological, because two theories that both successfully cover a given domain should have the same results in this domain by definition. Consequently, correspondence relations tend to be of the most practical interest when the success of one theory has not yet been demonstrated in this domain, and we thus articulate these relationships to demonstrate that it does indeed apply by virtue of its standing in these particular relationships to a theory whose success in this domain is already known. So correspondence is like a shortcut to results. We make these little relations rather than go through and actually derive everything out directly from the new theory in this old domain. So Heinz Post had the generalized correspondence principle, which generalized the relationship beyond quantum and classical mechanics. My statement of it here is that any two theories, which I'm here calling N and O, newer and older, not necessarily more fundamental and less fundamental, when their domains of success overlap, they must correspond to one another in these domains, meaning that at least one correspondence relationship must hold enough to convince us that the two theories really are consistent in the shared domain. So, what is a correspondence relation? Well, there's actually lots of different examples. Rader has 3 types, Hartman has 7, in a list that's not even supposed to be exhaustive. So I'm not going to go through them all today, but 2 big ones are numerical correspondence, when the two theories agree on the numerical values of some quantities. So an example is the recovery of the correct value of space-time dimension in causal dynamical triangulations in agreement with GR. There's also mathematical or law correspondence, where the two theories share some laws or other equations. An example is correspondence in string theory, where the background space-time containing the strings is shown to satisfy, or has to satisfy, the Einstein field equations, of course, from general relativity. Okay, so what is the point of getting these correspondence relations? As I've said, I take it there's only one goal, and that's establishing the consistency of the theories in the relevant domain, that they have the same results. But by virtue of doing this, correspondence plays many different roles in physics, which we can group into 3 general types: heuristic, justificatory, and efficient. And these correspond roughly to 3 stages of science: theory development, theory acceptance, and theory use. So in the actual paper, I've got 10 different roles within these 3 categories. And today I'm not going to, well, I'll mention a couple. So it's important in quantum gravity to understand these and their roles, because the heuristic and justificatory roles are, of course, also played by novel experimental data and empirical predictions of the theory and development. But in the case of quantum gravity, such data and predictions are notoriously lacking. So understanding these relations becomes especially significant to serve in these roles. So quickly, to give you an indication of the type of heuristic roles that correspondence plays, well, usually we think of it as going from the newer theory to the older theory, as in the case of the original correspondence principle. That's the justificatory role. We can also go from the older, well-established theory as a means of inferring parts of the theory in development from this established theory. So this is the explicitly heuristic use in theory development. So particular links between aspects of the old theory and aspects of the theory in development can serve as guiding principles. They can be taken as postulates, or they can serve in a role analogous to data. Some examples in quantum gravity of these heuristic roles, all approaches that take GR as a starting point. So all quantized GR approaches, including those based on path integral methods such as CDT. Another nice example is the role of background independence in loop quantum gravity. So it's a nice feature of GR that's singled out by loop quantum gravity and taken as a key guiding principle in the approach. It's retained in an analogous capacity in the theory. By doing so, the theory aims to recover GR. Very similar is the role of Lorentz invariance in causal set theory. Again, it's a nice feature of GR that's taken as a key guiding principle in the approach. It's retained in the theory, and thereby they aim to recover it in GR. So the justificatory roles are roles in theory acceptance. These can serve as constraints on theory development, as criteria of theory success. So this is part of the definition of what would count as the new theory, or they can be nice means of confirmation. These roles are about establishing the legitimacy of the new theory by appeal to the already established successful theory. So these are just an indication of the sorts of roles which I won't discuss. The 2 big ones that might be familiar to you, the role that the new theory preserve the success of the old theory, so that it's at least as successful as the old theory, or that the requirement that it explain the success of the old theory as well. But yeah, I don't have time for this today. Just want to point out the difference between the heuristic and justificatory roles. They can merge a bit. So again, thinking of the role of background independence in loop quantum gravity and Lorentz invariance in causal set theory, the theory's success in retaining or recovering these features of GR would serve also in the justificatory roles. So if we have aspects of the older theory that are retained in the newer theory, this can serve as non-empirical confirmation, as David said in his meta-inductive argument. And if we have aspects of the older theory that are recovered from the newer theory in the appropriate domain, perhaps unexpectedly, people take this analogously to predictions. But be careful, because having correspondence in one direction won't necessarily help you in getting it back the other way. So loop quantum gravity, causal set theory both have structures corresponding to spacetimes because they're constructed from spacetimes, but they both have difficulty in recovering spacetimes from these structures. Okay. So on to reduction. I like Josh's nice distinction between conception of reduction, which is a particular meaning that one attributes to the word reduction, and an approach to reduction, which is a particular strategy for showing that a given conception of reduction holds. So reduction 1 and reduction 2, the physicists and philosophers' sense is they can each be understood as either an approach to or a conception of reduction, as Josh has pointed out. And also following him, I take them both as approaches to reduction. And again, following him, I take them as approaches that attempt to establish the conception of reduction being domain subsumption. So showing that the new, more fundamental theory subsumes the domain of success of the older, less fundamental theory. So I would say that M reduces to L if all physical phenomena that are successfully described by the less fundamental theory are also described by the more fundamental theory. And using my conception of fundamentality that I presented at the start, so this is departing from Josh's ideas, that the laws of the less fundamental theory depend on the physics of M and not the other way around. So we can see that if M reduces to L, then M necessarily has a broader domain than L, because it subsumes the entirety of L's domain, plus whatever else it happens to describe. So hopefully we can see now that reduction, understood as domain subsumption, is just a special case of correspondence that applies when the overlap in domains of success of the two theories comprises the entire domain of success of the older theory. Also, unlike correspondence generally, this is an asymmetric relation. It only goes from M to L. So I'm using the physicist convention here in saying that M reduces to L. I should have pointed that out. Okay. So the more fundamental theory reduces to the less fundamental theory. But if you prefer the other terminology, you can just reverse that. Okay. Sorry. So unlike correspondence generally, a reduction only applies between more fundamental and less fundamental theories. However, it still aims at being a shortcut to results in the same way that correspondence does. And by virtue of this, it still serves all the same roles that I pointed out before, though it's less useful in the heuristic capacity because it only goes in one direction. Okay, so in quantum gravity, it's a criterion of success of the theory. So part of what it would mean for a theory to be quantum gravity, that it reduced to GR in the appropriate domain. So we must establish that quantum gravity reproduces all the successful results of GR. On the other hand, the theory may possibly be more fundamental than our standard model quantum field theories, but it's not, by virtue of being quantum gravity, expected to subsume the domain. So we could have a theory of quantum gravity that doesn't do this. However, if there is any case of overlap between the domains of quantum gravity and our quantum field theories, then we should establish some correspondence relationships there. Okay, finally, we're on to emergence. So the standard conception of emergence in philosophy of science comprises two claims. A dependence claim, where the emergent phenomena are somehow dependent on, constituted by, or generated by an underlying system or process. Sorry. And an independence claim that the emergent phenomena are somehow nevertheless autonomous from these underlying systems or processes. So in the case of quantum gravity, before getting there, there are two main conceptions of emergence generally in philosophy of science. Strong emergence, which holds that emergent phenomenon arises from some underlying processes, but truths concerning the emergent phenomenon are not deducible even in principle from the theory describing these processes. This shouldn't be the case in quantum gravity, or we really don't want this to be the case because it's a criteria of acceptance that reduction hold between quantum gravity and GR. So we're establishing these correspondence relations in the hope that GR is derivable in principle from quantum gravity. There's also weak emergence. So this is that the emergent phenomenon arises from these underlying processes, but truths concerning the emergent phenomenon are unexpected given just the theory describing these processes. Marc Bedeau's famous account is that something is weak emergent if it can be derived from the underlying processes, but only by simulation. So again, in quantum gravity, we really don't want this to be the case, because the point of correspondence relations is to be a shortcut to results, precisely to avoid having to derive all the results out of QG directly in the relevant domain. Okay, so the standard conception of emergence that's been adopted in philosophy of quantum gravity holds that L, here being GR, is emergent from M, here being quantum gravity, if M is more fundamental than L. So again, using my definition of fundamentality, that the laws of GR depend on the physics of quantum gravity. So this gives us the dependence claim. Also that GR, being the L theory, is novel and robust compared to the physics of quantum gravity. Novelty is that the two theories are somehow sufficiently different from one another, and robustness being that the less fundamental theory is largely insensitive to the details of M. So these are quite vague statements, but it's okay because this is just the conception of emergence. The approaches to emergence will then fill these in with particular accounts. So approaches to emergence in quantum gravity, they're developed by considering particular approaches to quantum gravity, so getting into the physics, comparing the fundamental structures described by these with those of GR. So in my book, I emphasize the robustness of GR spacetime due to its universality by various microstructures in quantum gravity in a way analogous to hydrodynamics, as Josh nicely mentioned for me. Chris and Nick, on the other hand, they emphasize the novelty, so the differences between quantum gravity and GR, due to one having space-time structures and local beables and the other one not. So, unlike the ideas of correspondence and reduction, emergence is not required in quantum gravity. But nevertheless, it seems like it holds. And this is because being quantum and being micro, the two ways in which quantum gravity is more fundamental than GR, are also ways of understanding theories being on different levels. Also, we have evidence for thinking that GR is robust. Obviously, it's incredibly successful, with unfortunately few hints of underlying physics. Also, the quantum corrections have been calculated, and these are minimal. All right, to wrap up, I've presented an account of fundamentality that doesn't imply reduction or emergence. I've argued that correspondence is very important in defining quantum gravity, and it aims at establishing the consistency of quantum gravity and GR, that the two theories have the same results in the relevant domain. And I've also mentioned the various heuristic and justificatory roles that correspondence plays in the search for the theory. I've presented reduction as a special case of correspondence, which is taken to apply by definition between quantum gravity and GR, and it aims at establishing that quantum gravity subsumes the domain of GR. Finally, I've argued that emergence isn't required, but it holds anyway thanks to the particular ways in which the theory is more fundamental than GR. So that's it. Thank you.
Comments will be given by Josh from University.
Thank you, Karen. I have two broad questions. The first one is two-parted itself. I think from your talk, I can guess the answer to the first part, which will lead directly into the second part of the first question. So oftentimes in theory of quantum gravity, there's this requirement that we recover general relativity in some appropriate sense, and this is one of the requirements that we set up here. This question I'm going to ask has to do with what do we exactly mean by recover general relativity in the relevant sense? We could imagine some advanced species coming and giving us a theory of the phenomena that we wish to model with quantum theories of gravity, which have nothing to do with our human, Earth-based general relativity. At least that's how it is that we formulate the theory. So let's say that this advanced species comes and gives us this theory, and for the life of us, we can't, in any real sense, reduce it to general relativity. It produces all the right phenomena at all the right energy scales. It explains to us much better than, it gives us a model for the beginning of the universe, for regions around black holes, for blank time scales, et cetera, et cetera. But we can't, the ontology of the theory is very different. We can't seem to map up the theories. Now, I think that most of us, and I'm pretty sure every physicist would be like, well, kind of screw the philosophers, criterion. We're going to use this. We're going to call it a quantum theory of gravity. It does everything that we kind of wanted a quantum theory of gravity to do. We don't know where general relativity fits into this cloud scheme. And I think I know where you're going to go with this, but I'll let you answer that question. So the question then is it really a necessary criteria for quantum theory of gravity for it to recover general relativity? Now, recover, as you said there, it's in scare quotes, so it's a vague concept. How vague can we make this concept so that it's consistent with this picture that I've, given us?
All right. So I guess this requirement of recovery is really human-based. And I would kind of want to go with what the aliens say, to be honest. Like, if they're telling us this is the actual theory and it does everything that we want it to do except for recover GR, I would not rule out that is your theory. Perhaps if it satisfies the other criteria. But the thing is, how would you know it's the theory unless you can actually get results out of it? And that's part of the heuristic and justificatory roles that correspondence play. So if you've got other means for fulfilling these roles that you're certain of, then maybe my schema is going to be dropped or modified a bit.
Sure.
Is that what you're expecting?
Roughly, and even at the end, you said you cashed out this idea of recovering the GR in terms of giving all the empirical consequences of general relativity. So if all we require to capture general relativity is that we get the sort of phenomena within the regimes in which general relativity is thought to apply, then we've quote-unquote recovered it. But if that's our case, if all we require is that we recover the phenomena of general relativity without any sort of derivation, or without, in a sense, more directly grabbing onto the theory in some more direct sense and just recovering its results, one then wonders, can we actually satisfy this other requirement that came up at the end, that we explain the success of general relativity? So oftentimes the idea is the fundamental theory is supposed to somehow explain why it is that the less fundamental theory worked, though technically it's false. And this is also a criterion that I question. Are we really required with our more fundamental theory to explain false theories? Maybe it worked because we have smart people doing experiments and making observations, and that's why it worked. Do we need a theory? What's this criterion of explaining false theories, and do we really require it? Especially if we have this gentleman here wants to answer, perhaps. His hand is going up. I'll let the moderator handle that. In any case, if it's the case that we actually, all we mean by recovering general relativity is that we get the right phenomena or get the right predictions in certain energy scales, can we really, or do we really want to hold on to this idea that we thereby have explained general relativity or why general relativity was true in those domains? I suspect that maybe you want to look at that criteria as well.
Yeah, thanks, Josh. That's really good, and I think that's kind of really what got me interested in exploring these questions, is that everyone takes this requirement to be, we need to explain the success of the theory. And it's something that I don't understand, and that's why I've started exploring it. I'm skeptical of it. Like, why should a theory who's known to be successful have to have its success explained?
By something other than the fact that it just works.
Which is just passing the buck as well, because how's this next one explaining it? Because it's also successful. But I'm still exploring this, and there might be more ideas that I'm very open to.
Thank you.
Thank you.
I first have a question about this criteria of robustness. Suppose I come up with a theory which is extremely meticulously designed, which very, very delicate aspects, each one of which I twinkle on the theory falls apart. But the theory, as it is designed with all those meticulous details, reduces to GR in all the known phenomena and explain and goes beyond ideals that say that it becomes singularity. You would think it's a bad theory because it's not robust, because if I twinkle any little detail of my theory, the whole thing falls apart. You would consider it a bad theory?
No, I would not consider it a bad theory. It's an interesting, so yeah, firstly it's not taken as a requirement, so that's part of the motive that we're saying isn't a requirement. But what's interesting is that the history of physics shows that this is how our theories are. Like, it seems like, yeah, using the framework of the particular theory shows us that this isn't the case. And so it seems reasonable to assume that physics will continue like this, or just keep turning out that successful theories that may have a reason because these don't filter down to these less fundamental ones. Yeah, it's interesting.
And then a comment regarding the question here, So you're imagining that this theory given by us, by agents, reproduces gravity probe B, Mercury, gravity waves, all the binary pulsars, all the tests we have of GR, and nevertheless we cannot formally deduce GR. That's what you have in mind. I would say that we face a puzzle like the mathematical puzzles that we believe to be true, like Fermat's last theorem that we all believe it to be true in the absence of that. I would say that we face that circumstance of the theory would nevertheless, for all we know, it deduces, there is a reduction, but there is a mathematical truth about it, supported by, empirically by the zillions of experiments in which things happen.
It's just that in the past it's been shown that this is how it works. Sorry, John.
Oh, well, thank you. I would say that the point is well taken. We might believe that there is such a derivation, like some formal derivation in general relativity from this advanced species. But the very fact that we don't have it shows that it's not a requirement for acceptance. We don't have it. Maybe it'll show up, but we don't require it to accept it. We're all going to go on and use this advanced alien species to travel to interstellar planets. And we have philosophers in Yale and Harvard, saying they're not going to accept it. I'm just picking on Yale and Harvard.
So, I guess I was wondering how much the critique of weak emergence in this context was going to generalize weak emergence throughout physics. Like there was anything very specific to quantum gravity in the critique of weak emergence. One thing that some people might have had in mind by weak emergence is something like when you look at the fundamental theory, you don't expect the non-fundamental stuff to come out of it. It takes a lot of thought and a lot of reasoning and maybe some heuristic steps before you can get there. So maybe the problem is with the definition of weak emergence, not with the kind of using something like weak emergence to understand what's going on in quantum gravity.
Yeah, so that's interesting. But so yeah, I think this is more generally, we kind of just don't want weak emergence. Like it might nevertheless be the case, but we prefer not to have it. But as you said, it may nevertheless hold anyway. And also, so that you repeat the last one.
I was just thinking that maybe even if this kind of critique of that notion of weak emergence does apply generally throughout physics, there might be something in the vicinity which is still an interesting notion, which is something like it takes a lot of hard work and it's totally non-obvious that we're going to get something like a higher level theory out of a lower level.
Okay, so this seems to definitely define quantum gravity as physics work has shown with the novelty aspect. So you're right, maybe this novelty aspect
defined fundamentality in terms of dependence, but then dependence is quite a complex notion on its own. So could you say a bit more about what dependence means here?
Yeah, I guess I'm just working in the intuitive sense. So it's kind of just that one. I guess by example is the best way to do it. But the different ways in which so effective that we can scale it both ways using our framework. But the way the flow shows that it only goes in one direction. In terms of dependence, one affects the other, however minimal it is, independently. So something like this. So yeah, I guess I mean some sort of metaphysical dependence, not necessarily causal, but
So you mean this kind of came up with Joshua's talk as well. You mean something more than just the existence of a mere function that's relating points of one state space to another. There has to be some sort of physically meaningful, I hesitate to say salient kind of feature of the function that sort of there's a physical story about why these lower degrees appear as these. Yeah. Okay. Thanks.
Josh?
I'll just talk about it. I can't catch up on that. I was thinking about this for Karen as well, what dependence might be in. Oftentimes in a metaphysician sense, if we're not using it causally, we do it counterfactually. So we think about, the closest possible worlds in which one thing is true and the other thing is not true. So theory A is more fundamental than B if in all the closest possible worlds where B is true, where B is false, A still happens to be true. I.e., A's truth isn't dependent on B being true. So we say that A may be more fundamental than B. But, in these cases of counterfactual, so think about the one where we had it here with special relativity and general relativity. The claim here was that general relativity was more fundamental than special relativity. But we analyze that in terms of counterfactual. So let's go to the closest possible world in which special relativity is true. The claim then is that general relativity should still be true. I have a hard time imagining that, right? All the closest possible worlds in which special relativity is true, it also seems to be the case that general relativity would be true. In which case, we wouldn't get the fundamentality result. At least, how does one analyze the space of all possible worlds and which ones are closest to them? I don't know. But this is my own intuition notion. So if we use a non-causal sense of dependence to do it counterfactually, I don't know whether or not we get the asymmetry that we need for the definition of fundamentality. So this is, you might want to go with counterfactuals, but I don't know how to do it right, because I'm not getting the asymmetry.
Can you explain again what we have done?
So let's say that one says theory A is more fundamental than theory B, just in case in all the closest possible worlds in which theory B is true, or theory B is false, theory A remains true. So you think about all the worlds, so let's think about, in this case, quantum mechanics and Newtonian mechanics. You say quantum mechanics is more fundamental than Newtonian mechanics. Well, why is that the case? Let's go to all the closest possible worlds in which Newtonian mechanics is false. Quantum mechanics might still remain true. At least that's the intuition behind this counterfactual approach. And this not counterfactual, the counterfactual definition of dependence, right? When one thing depends on another. If it doesn't depend on it, then you should be able to change the truth value of it and the thing remain true, for instance. Right? So for instance, me being in this room is independent, presumably, of my gender. That being the case, we'll go to all the closest possible worlds in which I happen to be a female, and we'll see whether or not I'm still in this room or not. And if it's the case that I'm still in this room, then we say that my gender, me being in this room, is independent of my gender. So this would be a counterfactual definition of dependence. But in this case, with respect to physical theories, I don't see the asymmetry working out. In particular, if I go to the closest possible worlds in which, for instance, special relativity is false, those possible worlds are also worlds in which I imagine general relativity to be false. reversal
Because they're
in that
classical
case.
worlds instead of quantum worlds.
Right. Yeah, so it's worse than that.
So it's especially kind of, it's something that I definitely need to look at, this idea of fundamentality. Because, like, taking it as part of reduction and correspondence, but actually people typically appeal to the reduction and correspondence relationships themselves in order to establish the dependence of fundamentality, which, as you point out, is not actually in necessary. So, yes, that one I investigate.
Presumably the classic worlds are not the closest worlds.
They're not the closest worlds in which quantum mechanics is false.
Yeah, we're the freaks.
Quantum mechanic worlds, which are more classical, are closer than non-quantum classical worlds.
But by Josh's case, I was just reversing it for the dependence. So I want to go to a case where quantum mechanics is false, and I think classical mechanics is still correct.
What I say is that those worlds will be further away than we know we are.
Made a statement about it's not required that QFTs emerge from this quantum gravity theory that we have. So what do you mean by QFTs?
Just the standard model.
Okay. So but there are also essential consistency conditions on how matter can be coupled together. So those are important in the quantum gravity theory.
Okay, I guess, yeah, what I have in mind are quantum gravity models that are not like strict theory.
Right, so not unification, but still some consistency.
I think we still need to include that, and so far I have still working. But yes, you're right. It's not supposed to be pure, right?
Right.
Okay.
And just about this point about whether we can have GR and not special relativity, we can have a different local group, right? In a different universe where GR is still true, but in the local unit, your group is not in cosmic symmetry, but something else, let's say this or something. And in that case, that is the universe where SR is not true, but GR is true.
Karen, could you stand by the mic over here, sir?
I mean, away from the bowling machine.
I have a question as well. I'm a little bit mystified as to why you and maybe Josh are mystified why explaining success.
It's weird.
Why? So, I mean, let's not worry about probability, but instead go to sort of more established cases where, for instance, you have a Newtonian gravitational theory which gets supplanted by GR as a more fundamental, better description. Now, it seems obvious that unless GR can explain to us in some complicated way, using the sort of relations that you've sketched for us, why Newtonian gravity was as successful as it was, because otherwise that success would just be miraculous happenstance. It's amazing that Newtonian gravity worked as well as it did in those cases where it did, unless the more fundamental theory could explain to that. So I think to me, it's a very natural idea that you would want the more fundamental theory to explain that.
No, I feel like if a theory is successful, then comparing it to another successful theory, what is that going to give you above the success of the theory already?
Because in the case of Newtonian gravity and GR, presumably when we say that GR is more fundamental, we thereby mean to say something like Newtonian gravity isn't really true. That's not a true theory. Maybe GR is, maybe not, but Newtonian gravity is not true. Now, why was it, did it work as well as it did, if it's not somehow close to the truth, or getting some things kind of right, in a way that neither hopefully true or potentially true fundamental theory can explain.
So it's just to ease our minds a bit, conceptually, that our theories are telling us something true about the world and we're getting closer each time. I think you're building in a lot of realist assumptions that may or may not be justified, and I think it's we need to look at those and why we believe this, why it seems so conceptually nice for us to believe this.
I do think that this is a realistic picture. Any other questions? And I forgot to provide a number of
Always perhaps counter something to your idea. There was something of the Keplerian, or this idea that somehow the classic solids, the platonic solids, has some information about the orbits of the planets. Apparently, if you look at the first 6 or 7 planets, things fit well, but Newtonian theory does not explain that.
Okay. In that case, so I guess if there's a situation where I have a more fundamental theory, then I come to make a decision whether I want to just give up the old theory because that's complete rubbish and it is off the track, or to say something more realist and say, there's a sense in which that theory got some things absolutely right. If it's the latter, then I need to have an explanation in terms of more fundamental theory. If it's the former, then no.
Yeah. To tie it into my paper with Niels, it may be that quantum gravity as we have it, because it's not, fundamentally unified theory, including, all the standard models, it may be that it's just a stepping stone to an actual fundamental unified theory, and maybe that one's the one that gets it all right and true. So the matching up of an intermediary theory might be a bit strange requirement too. And check out our cool paper together.
It's just a concept of the separate. So consider a case of independent gravitation or say geometries of gravitation, GR. Of course, you may expect that GR explains to you why independent gravity is a successful field. But is it really GR which explains, or is it a set of mathematical assumption in PhD, something like Feldman's recovery theory? So perhaps it's not really the job of the theory to explain that, but rather a set of additional mathematical approach which does that.
So I'm not giving you the talk, I'm questions, but I think it's still the theory plus maybe some additional rigid principles or additional assumptions.
But since I have a microphone, I wanted to ask a clarification question. So at some point early on, you said that you take special relativity and GR being on the same level. I just don't understand that.
Yeah. So that's, yeah.
So perhaps just 1%. So of course there's a sense in which special relativity is just one of the special GRs. Okay, how do you
Yeah, that's essentially what we had in mind. But basically, we're trying to think of examples where you could have reduction without emergence, and this seems to be a nice case of that. So the idea of theories being on different levels, so they're both describing the same phenomenon or system, say, and it may be that the less fundamental theory describes the particular phenomenon, and the more fundamental theory describes the system at a different scale, energy scale, or maybe quantum rather than a classical, but still the same system, right? Hang on, I'm confusing myself. Exactly. This is how they cannot be on the same level. So, exactly. A less fundamental theory that's on a different level from a more fundamental theory may describe some phenomenon, whereas the more fundamental theory that's on a different level may describe just the physics underlying that phenomenon. So that's how we have different levels, and I think, the case between special relativity and GR is not a case of this. So they're better understood as being on the same level. Does that make sense?